Okay, this is pretty much everybody we're going to have the privilege of seeing. Okay, so today is basically autonomic nervous system. So this motor system is another one term for it. The autonomic system has a couple components. One's the motor system, and it's a big part. It involves basically activities of smooth muscles, cardiac muscles, and the glands. And there's a couple of divisions of the system, sympathetic, parasympathetic. And there's another system which doesn't get a whole lot of press time, and not as much as known about it, which is the enteric nervous system, which is also an autonomic system in that it acts by itself without any conscious input from the person. The whole framework is controlled by the hypothalamus and the nuclear reticular formation within the sort of the lower brainstem, except for the enteric system, which is independent. Differences from somatic motor. There's some somatic motor being basically the system set up to move your body at will on the cortex. So the anatomical and functional divisions of the visceral system, the thoracolumbar is sympathetic, and the cranial nerves as well as the sacral nerves contribute to the parasympathetic nerves. There'll be some diagrams of this. Lower motor neurons are outside the CNS as opposed to in the spinal cord, which you can see with somatic motor. They are near the spinal cord for the sympathetic and the sympathetic chain, and they're near the target organ for the most part, the parasympathetics. Sympathetics also have some slightly more distal ganglia where it goes through the chain and out to the ganglia. There's a lot less sort of organized structure at the target. Bear in mind, we're not really in the nervous system anymore, so you might expect a little less structure. And central control is a little bit less localized. See some of that hypothalamus. Effects tend to be by neurotransmitter and receptor. And there's some unique things about that, the muscarinic system being one of them, cholinergic system being another component of it. All right, so this is it's a little hard to see, but I think you can get the idea. You've probably seen this before in one version or another. The sympathetics on the left and the parasympathetics on the right. Parasympathetic coming from the third nerve, the ninth nerve, and the 10th nerve, as well as the sacral nerves, and then you have the thoracolumbar chain on the sympathetic side. The end organs are shown here. These little things are little ganglia in between. They tend to be closer to the spinal cord for the sympathetic, and much closer to the organs, as I try to pick here in the parasympathetic side. This is actually color coded, so the cholinergics are blue, and then the PREganglionics, the POSTganglionics, cholinergics are purple. You can't see it so well, but this is a purple. And then again, PREganglionics would be cholinergic, and then for the sympathetic, you have the more adrenergic extensions out to the end organs. Go into a little more detail on neurotransmitters in just a second. Sympathetic division, the preganglionic neurons are in intermedial lateral column of the lateral horn. So here's the lateral horn going down that way, and right there, little bulge. And that's from T1 through L2 or L3. So quite a distance. Sympathetic nerves have the paravertebral sympathetic chain close to the spinal cord, just outside the vertebrae. And then the ganglia are in plexuses, a little bit closer to the organs. Postganglionic axons are not myelinated. This is why they are the gray conglomerates, which you see again on the next picture. And they get out to their targets by hopping back onto the spinal nerves. Postganglionic axons go from the plexus straight to the viscera. So the postganglionics these are going straight to the viscera. This is the sympathetic chain, again, just outside the spinal column, so to speak. And it's lengthy, going from upper thoracic down to early lumbar. The gray ramus is right here, and that's only unmyelinated postganglionic neuron going out to the target. If it goes to a ganglion otherwise, then it will go directly to the ganglion without hopping back onto the spinal nerve. Dorsal ganglion's over here for reference, so this is ventral side, this dorsal side. The sympathetic trunk does go up and down a little bit beyond the levels where nerves enter, and that allows for passage of information to other parts of the body. Parasympathetic division, cranial preganglionic fibers come from Visceral, 3, superior and inferior salivatory, bonds in medulla, sensory 9. Visceral motor division, the ambiguous in medulla, that would be mostly 10, and dorsal motor is also 10. Sacral preganglionic fibers form the lateral, come from the lateral gray matter and spinal cord. The parasympathetic ganglia are again much closer to the target organs, so a little bit different than the sympathetic system. Here's the parasympathetic. It's a little hard to see here. Here's Edinburgh Westfall right up here, back of the midbrain. And in here are the nucleus ambiguous. It's ambiguous and okay, keep going forward. Enteric nervous system is a bit different. Let's back up. Sacral preganglionic fibers, gray, I did mention that. Parasympathetic division. Again, we sort of looked at this. It's a little bit different in that there's no on and off the nerve. You're sort of go close to it, but jump right off, go out to the ganglion and then onto the and things are coming from little tiny nuclei running close to the lateral area of the gray matter in the spinal. The enteric nervous system is quite unique in some ways. It's probably one of the oldest nervous systems in that these are present in simple organisms as well. They're basically the neurons that push along the contents of the gut and control the activity of the gut, but they invest the lining of the intestines and operate sort of independently. My enteric plexus is involved somewhat in muscle control. It's probably used for things like moving the bowels. Meissner's plexus is for chemical monitoring and then secretion, less sort of conscious. This is to show a little bit where the plexus actually is. It's in the linings, a little closer to the surface. The outer surface being right here and the villi being on the other side. And here's Meissner's plexus on the inside. If you look at it this way, these plexuses are sort of in the wall of the viscera itself. The sensory components, these can relate to both parasympathetic and sympathetic. The afferent fibers going through the dorsal root ganglion for the parasympathetic system. We're talking about the glossopharyngeal vagus nerve. A central target is the solitary tract for the parasympathetics. Sensory afferents via sympathetic nerves to get to go out to the receptors, and the autonomic reflexes are mediated by the primary visceral sensory axons determined with the lateral horn and spinal cord. So the reflexes. I think we'll get into one of these with some of the examples of the sort of autonomic function. Okay. Sensory components do contribute to some pain. You get referred pain because of location in the dorsal horn where these nerves are coming in. And you go up to the thalamus, and that's when I think the signals get really crossed. In the brainstem, the targets for the visceral afferents are the nucleus of the solitary tract and the reticular formation. In the dorsal column pain pathway, there are some nuclei along the way, ocellus and cuneatus, deeper in the medulla, also involved, and they project upwards towards the thalamus. Input from thoracic and abdominal organs, head, neck, and all that is for the cranial nerves. And usually only painful sensations are actually felt. So, for instance, you're not going to necessarily feel like blood pressure is too high or too low, other than actually physically dizzy. But you're not going to feel it in a viscous one or so sensory components coming in here through the glossopharyngeal and the vagus, coming in through the solitary tract, and then again they project upwards. There's a solitary tract at various levels. The efferents going out and over here. Sort of more lateral portions. Central control. This is the postulated mechanism that the brain actually controls the autonomic nervous system. Caudal nerve of the solitary tract projects to lots of different places. It goes to primary visceral motor, which is the nerve coming out of the nucleus ambiguous. It goes into the vagus nerve. And then there's also a projection towards the medullary reticular formation, which is basically the premotor area. And the amygdala itself seems to integrate, that makes sense. Amygdala sort of involved with emotion, a lot of sort of gut feelings and things like that. There's a reason for that word. Hypothalamus is also integrated into this control system. I'll go into that a little bit. The area where the output is controlled is actually the bottom, sort of anterior portion of the hypothalamus. And then the parabrachial and brachial conjunctiva, very close to the hypothalamus. Okay. The primary visceral sensory cortex. The brain itself is the posterior insular cortex. So back part of the insula, posterior part. So it'd be edging towards the parietal area. Primary visceral motor is medial prefrontal. So a little bit anterior to the same areas. And input from other sensory modalities and higher cognitive centers result in what's called the autonomic network. I think I have a picture of that. Hypothalamic targets are the reticular formation, including what's called premotor circuits, and then the PREganglionic nerves, which are down in the spinal cord and in the brain before the cranial nerves. Here's the circuit. And as you can see, it's a lot of stuff coming in. These are the inputs coming in. Nucleus of the solitary tract then projects to many different components we just talked about. The paravertebral nucleus is actually parabrachial nucleus. It's close by. It projects to the hypothalamus. It's actually kind of straddling the hypothalamus. You can see there's quite a bit of feedback back and forth there between these different structures. All right, let's go into some of the mechanics. PREganglionic neurotransmitter is acetylcholine for both sympathetic and parasympathetic. I think we touch upon the other system, just a moment, the Enteric system. The nicotinic acetylcholine receptors are different from muscarinics. Got this from basic neuroscience. Nicotinics are ligand-gated ion channels, and they have a very fast excitatory potential. Muscarinics are G-protein coupled. It's slower and has a bit more in the way of metabolic and sort of functional consequences. It ends up enhancing excitatory potentials. Potentially, neuropeptide co-transmitters are also used by a lot of these cells, as well as extensively in the enteric system in the gut. Postganglionic neurotransmitters. Here's where we get a little bit of variability. We get both norepi and acetylcholine, and then the different targets depending upon which system is being used and where the target happens to be. So the norepinephrine, noradrenergic targets are the alpha and beta subtypes. Ones that famous for beta blockers and alpha blockers. Acetylcholine activates again nicotinic receptors, which can be also in the postganglionic nerve cells as well, or the targets. Then there's the muscarinics, and they're present in the target organs. Sympathetic input also goes to the sweat glands via acetylcholine rather than norepinephrine. So that's a little bit of a variation there. Just a footnote, the nicotinic is present both in sort of the first step into the ganglion as well as at the target organ. Okay, you can't see this one as well. This is just the alphas and betas, the different tissue targets and the effect of epinephrine on those particular organs. Sorry, it's not bigger. Includes the smooth muscle, heart muscle, salivary glands, etc., kidneys, adipose tissues, and alpha-2, heart muscle again with the beta-1, and then a skeletal muscle has some betas, beta-2s. Okay, these are cholinergic, as you read. Nicotinics are present in a lot of the targets. It depends on the particular site. And the response is fast, but it's got such a variable target that's not able to really put up with that. Muscarinics are mostly in smooth muscle as well as cardiac muscle. And threes are funds.
Yeah. There's always going on. There's always something going on in there.
Yep.
I'm sorry, I'm so sorry, Mr. Talk.
It's okay.
Oh, okay, awesome. Thank you.
Okay. So these are just some of the results or activities of the acetylcholine out on the peripheral targets. These are actually the nuclei in the thalamus. This is to give some idea of the complexity. The actual nuclei involved with the output tracks, particularly going pituitary or right here, supraoptic, paraventricular. This is a three-dimensional thing, and it's not quite to scale, so to speak. This is actually a lot closer than it looks. This bottom one sort of wraps around like a U. There's some nuclei closest to the ventricle are also pretty heavily involved in the activities that we're trying to control here. Okay, so Horner syndrome. So this is sort of the evidence of irritation of sympathetic input to the eye via the third nerve, and I'll go back and look. Here. So let's look at the chain. Right. This is the sympathetic chain going on to the eye. The role of the sympathetic nervous system in the eye actually is to dilate the pupil, and to some extent it may also have a little bit of effect on glands and sort of the sweat tone, the skin tone. So sympathetic input will make the skin more sweaty. So if you cut off the sympathetic input, your pupil will actually constrict a bit, and the sweat will disappear. And those are two of the features of the hormones. So, You also see a little ptosis there. This pupil is actually a little smaller. It's pretty minimally small compared to this, but that's how it's supposed to be. You can't see it more dramatic at certain times. The cardiovascular regulation is also carried out by the autonomic system. And this is a pretty good example in the sense that the two opposing systems are kind of intertwined and interacting with each other. So the afferents that are involved with the baroreceptors in the heart and major blood vessels will go back through the vagus, the chemoreceptors, the carotid body. That was so glossopharyngeal and vagus go back into the solitary tract, carry that information, and then the sympathetic innervation comes out basically through the usual pathway and adjusts the pace, tone, sort of strength of the heart. Parasympathetic sort of does the balancing act with the other way around. So, to give an idea here, your afferents are coming in. This is a baroreceptor here at the looks like the pulmonary arteries, and then this one is sympathetic. Okay. So yes, this is also sort of a baroreceptor, and they both go back in. They adjust the signal. There's a bunch of intubation of signals, is probably a good term for it. And then the signal goes back out through to the heart, which is regulated right here. And the other symptom through the sympathetic tree, go out through the sympathetic chain and out to the heart directly. These are the sensors. This is the actual ethernet right there. The end result is that the vagal tone will basically decrease your heart rate, and the parasympathetic tone will increase it. The vagal will decrease your heart rate, and sympathetic will increase it, which makes sense. The urinary regulation. It's also a bit complicated in that the receptors, well, the two systems are integrated and complementary. Sympathetic tone basically relaxes the muscles of the bladder itself, so that you don't have to void right at that moment, because when the sympathetic system is active, you don't want to be taking the time to do that in this dangerous situation. So sympathetic tone relaxes the bladder, whereas parasympathetic tone increases the bladder tone and causes need to go to the bathroom and promotes voiding. So the parasympathetics are coming off the sacral plexus through the pelvic plexus, and bladder wall contraction is mediated through both the internal sphincter and the bladder tone itself. So it's a little paradoxical. Sympathetic tone is stimulated by the distension of the bladder wall. You know what? I think this thing's that's backwards. I'm sorry. Because sympathetic tone actually would not be stimulated by the distension of the bladder wall. Parasympathetic. So I think I better redo that slide. Urinary regulation. Full bladder increases parasympathetic activity, which we're just correcting, and decreases sympathetic activity. And then you get tonic somatic motor activity, which is basically straining to void. That you can, if you keep tonic activity on the pelvic floor, will prevent urination, and then you can release it with a parasympathetic surge. Okay, so just to footnote, paraplegics have decreased defective central control, so things are a bit more on auto reflex, and that doesn't always work quite so well. And it's hard to initiate things because you can't send it down to the brain. Urinary regulation. Here's the bladder with the sort of efferent going in through the muscle. This is actually efferent. This is an afferent bladder, reversal of ganglion. Here is an efferent going out through the little sphincter right there. That comes through the sympathetic chain. And the parasympathetic chain is controlling more of the bladder tone, as is the sympathetic chain in parallel. A little complicated. And we have a similar sort of balancing thing going on with the sexual function for men and women, as it turns out, with the sort of a balance of parasympathetic and sympathetic. So parasympathetic is primarily active during excitation, and then during orgasm and ejaculation, that's when the sympathetic kicks in. Summary. Autonomic ganglia innervate lots of smooth muscle, cardiac muscle glands, sort of complementary antagonistic effects, which allows sort of yin-yang type phenomena. Inference from dorsal root ganglion and cranial nerve sensory ganglion to the mucus of the solitary tract. It's the main afferent pathway. And descending control comes from thalamus, hypothalamus, brainstem reticular formation. PREganglionic neurons and autonomic ganglia are in different locations, depending on which systems. Diverse functions are basically a result of sort of mixing and matching receptors, as well as the effects of the receptors in target organs, which allows you to do quite a bit of diverse things that are kind of coordinated. And that's an interesting way to sort of get a lot of function out of the simple system. Sorry, any questions? No. Okay, everybody's sleeping. No, it's okay. This is the change. Oh, I can't correct you. That's right. Sorry. This is just a read on the copy. So,
if you can exit this presentation, you want to edit the text.
oh, I can't edit it because I actually have it open in another.
Oh.
I'd like to. But I'll have to go over it.
It doesn't appear as. You cannot edit. Did I edit this? I mean, with these glasses, I can't see anything else.
It says read only.
Yeah.
Oh, it does?
Yeah.
That's right. Yeah, I mean, I can't see those.
Okay. I'll be able to do it when we get back. The methods research, you guys did this, like part of neuroanatomy and all that as well. Yeah.
We just got a 2-pack call person.
Oh, okay.
If you wanted to.
Wait, was that one we left earlier? or-
There's another 68544.
That one was called Diane, I think. or-
Usually it's.
Thank you, Doctor.
Okay.